Hello student, today we will discuss electrostatics of a conductor. In our previous class we have discussed about electric field, potential and potential due to charge. Field also we have discussed. Today we will discuss the basic properties of a conductor. And first property is what? Inside a conductor, electrostatic field is zero. Or electric field inside a conductor is zero everywhere. So total charge, net charge inside the conductor will be zero. Therefore the field will be zero. Then second property, at the surface of a charged conductor, electric field must be normal to the surface. Under electrostatic condition, once the charge on a conductor are rearranged, the flow of charges stops. Therefore, component of electric field along the tangent to the surface of the conductor must be zero. That is E cos theta equal to 0, where theta is the angle between electric field and the tangent. E cos theta is 0, so theta is 90 degree. Now this is the third property. The interior of a conductor can have no excess charge in static situation. The excess charge can reside only on the surface in the static situation. Whatever be the static charge or excess charge, it will remain on the surface of the conductor. There will be no excess charge inside the conductor, hence the electric field will be zero. These three properties are very interlinked property or very same. Now the fourth property of a conductor, electrostatic potential is constant throughout the volume of the conductor and has the same value as on its surface. So it is very simple question that if field is zero, because Q is zero, so what is the potential? From this definition of potential, V equal to Q upon 4 pi epsilon 0 R. What will say? That potential will be 0 if Q is 0. But this is not correct. We know that electric field is negative gradient of potential. Since E is equal to 0, minus dV by dr equal to 0, dV equal to 0, then integral of dV will be equal to integral of 0. Integral of dV will be constant V, so V is equal to constant. Inside the conductor, potential is constant. What does it mean? If we bring a charged particle from infinity, then we will require to bring the charged particle from infinity to the surface of the conductor. and that work done will store in the form of potential. Say for example, if here V equal to 10 volt, that means V equal to W by Q. Q is 1, so we will require 10 joule work to bring unit charge from infinity to that point. Now inside the conductor there will be no charge. So since we don't have any charge inside the conductor here, no charge, so what will be the potential? There will be nothing which will oppose, so there will be no work from inside the conductor, either to move up to B point or to move up to A point. We will not require any work, but we will require work till the surface. So inside the conductor, the potential difference between point A and point B will be 0. Hence, the net work done to move from point A to point B inside the conductor will be 0, because these 2 points are at the same potential. So when the points are at the same potential, we will not require any work. Okay, hence the potential inside the conductor is 0. Then we have another property. The electric field at the surface of a charged conductor. It is E equal to sigma upon epsilon 0 and cap, where sigma is charge density and n cap is unit vector normal to the surface in the outward direction. Let us consider a short cylinder of small area ds. Area of cross section is ds, delta s, and negligible height. This cylinder is partially inside the conductor and partially outside the conductor. So just inside the conductor, electric field will be 0. What will be the field just outside? So the flux passing from delta S area, E dot ds, E into A, from the that definition, E into A, E dot delta S. And we know from Gauss law, phi equal to Q by epsilon 0. So left hand side of equation 1 and equation 2 are same. Therefore, E dot delta S equal to Q by epsilon 0. You can replace Q by sigma into delta S. Why? Because sigma equal to what? Q by ds. So when you replace this, Q will be what? Here you can write sigma into delta S. Then this equation will become like this. This is E dot delta S equal to sigma delta S. This delta S cut. So E equal to what? Sigma by epsilon 0. E equal to mod of sigma upon epsilon 0. Sigma is greater than 0, then electric field will be outward because it is positive charge, and sigma is less than 0, electric field will be inward for negative charge. So this is another property, E equal to sigma upon epsilon 0 dot n cap. This is the electric field just outside the conductor. Now we have one more property of a conductor, electrostatic shielding. Consider a conductor with a cavity with no charge inside the cavity. The electric field inside the cavity is 0. We have proved already electric field inside a spherical shell So E is 0 inside the cavity. That does not mean that V will be 0. V is not equal to 0. E is 0, V is constant. And very similar, very famous example for electrostatic shielding, that cavity inside the car. You are sitting in a car and car is moving in a forest or jungle, and then lightning occurs, then excess charge will remain on the surface of the car. If the windows and gates are closed, then charge will remain on the surface of the conductor, that is on the charge on the car, and we will remain safe. We will not get any electric shock. Okay, so these are the basic properties of a conductor. The metallic body of the car or bus provides electrostatic shielding from lightning. The fundamental fact is that electric field inside a cavity is zero. Whatever may be the size of the cavity, shape of the cavity, whatever may be the charge on the conductor, but inside the cavity, electric field is zero. So you do this much, okay?